NEC 250.52. A1 permits the use of a metal water pipe as an equipment grounding conductor if the pipe is at least 5 feet long and has a diameter of at least 1/2 inch. NEC 250.53. E allows for the use of a single grounding electrode, such as a ground rod, as the sole connection to ground for a service with a grounded neutral conductor if the grounding electrode conductor is number 6 AWG or larger. NEC 250.66 refers to the grounding electrode conductor, or GEC, that connects the service panel to the grounding electrode. The size of the GEC is determined by the size of the overcurrent protective device, or OPT, for the service, and it must be at least number 6 AWG. If the 200 amp service panel is likely protected by a 200 amp breaker or fuse, then according to NEC 250.66, the GEC for a 200 amp service must be number 4 AWG or larger. However, NEC 250.53 D2 states that, where supplemental electrodes are used, the grounding electrode conductor size shall be determined from the largest size required by any of the electrodes used. In the case where the supplemental electrode is the metal water pipe, since the metal water pipe is at least 5 feet long and 1/2 inch in diameter, it can be used as an equipment grounding conductor without the need for a supplemental GEC. Therefore, a number 6 bare copper wire can be used as the EGC from the panel to the water pipe, and it is sufficient. It is important to note that the requirement for a number 4 AWG GEC applies to the grounding electrode conductor that connects the service panel to the grounding electrode, not to the EGC that connects the panel to other grounding electrodes such as the metal water pipe. Considering grounding electrode conductors, or GECs, and equipment grounding conductors, or EGs, it's crucial to understand their distinct roles within an electrical system. The GEC is the conductor that connects the service equipment, typically the neutral bus in the service panel, to the grounding electrode system. This system can consist of various electrodes, such as ground rods, metal water pipes, or concrete encased electrodes, often referred to as UFA grounds. The primary function of the GEC is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses during a ground fault. The size of the GEC is determined by NEC Table 250.66, which correlates the size of the service entrance conductors or the equivalent area for parallel conductors to the minimum required size of the GEC. It's important to note that the GEC isn't intended to carry continuous current under normal operating conditions. Now let's discuss equipment grounding conductors, or EGs. EGC connect the non-current carrying metal parts of electrical equipment such as enclosures, raceways, and appliance frames to the grounding system. The purpose of the EGC is to provide a low impedance path for fault current from these metal parts back to the source, again ensuring the quick operation of overcurrent protective devices in the event of a ground fault. EGC can be wires, such as copper or aluminum conductors, or metallic raceways, such as rigid metal conduit or electrical metallic tubing. The size of the EGC is determined by NEC Table 250.122, which bases the EGC size and the rating of the overcurrent protective device protecting the circuit. It's important to differentiate between the functions of the GEC and the EGC. The GEC connects the service equipment to the grounding electrode system, while the EGC connects the non-current carrying metal parts of equipment to the grounding system. Both play crucial roles in ensuring electrical safety by providing low impedance paths for fault currents, but they serve different purposes and are sized according to different tables in the NEC. Understanding the purpose and sizing requirements for both GEC and EGC is essential for safe and compliant electrical installations. Now, let's delve deeper into the specific requirements for using metal water pipes as grounding electrodes. As mentioned earlier, NEC 250.52. 8.1 permits the use of a metal water pipe as a grounding electrode if certain conditions are met. Firstly, the water pipe must be in direct contact with the earth for at least 10 feet, although the code specifies 5 feet. This requirement ensures that the water pipe is effectively grounded to the earth. Secondly, the water pipe must be electrically continuous. This means that there should be no insulating joints or breaks in the pipe that would interrupt the flow of fault current. If there are any such discontinuities, they must be bypassed with a bonding jumper. Thirdly, the water pipe must be supplemented by an additional grounding electrode, such as a ground rod or concrete encased electrode. This supplemental electrode provides an additional path to ground in case the water pipe becomes ineffective. The supplemental electrode must be bonded to the water pipe with a bonding jumper. The size of the bonding jumper is determined by NEC Table 250.66 based on the size of the service entrance conductors. It's important to note that the metal water pipe must be continuous all the way to the earth. This means that the pipe cannot be interrupted by plastic or other non-conductive materials. If there are any non-conductive sections of pipe, they must be bypassed with a bonding jumper. When using a metal water pipe as a grounding electrode, it's also important to protect the pipe from corrosion. Corrosion can increase the resistance of the grounding path, making it less effective. To prevent corrosion, the pipe should be coated with a corrosion-resistant material such as paint or epoxy. Additionally, the connection between the grounding electrode conductor and the water pipe should be made with a corrosion-resistant connector. The connector should be listed for direct burial, meaning that it is designed to withstand the harsh conditions of being buried in the earth. Finally, it's important to inspect the water pipe regularly to ensure that it is still in good condition and that the grounding connection is still intact. If any signs of corrosion or damage are found, the pipe should be repaired or replaced. Let's explore the concept of supplemental grounding electrodes in more detail. As we discussed earlier, NEC 250.53 D2 requires that metal water pipe electrodes be supplemented by an additional grounding electrode. The purpose of this requirement is to provide redundancy in the grounding system. If the water pipe becomes ineffective for any reason, the supplemental electrode will still provide a path to ground. There are several types of grounding electrodes that can be used as supplemental electrodes, including ground rods, ground plates, and concrete encased electrodes. Ground rods are the most common type of supplemental electrode. They are typically made of copper or copper-clad steel and are driven into the earth. Ground plates are similar to ground rods, but they have a larger surface area in contact with the earth. Concrete encased electrodes, also known as grounds, are made of a length of bare copper conductor that is encased in concrete. grounds are typically installed in the footings or foundations of buildings. The choice of which type of supplemental electrode to use will depend on the specific site conditions. In areas with rocky soil, it may be difficult to drive ground rods. In these cases, ground plates or grounds may be a better option. Regardless of which type of supplemental electrode is used, it must be bonded to the water pipe with a bonding jumper. The size of the bonding jumper is determined by NEC Table 250.66, based on the size of the service entrance conductors. It's important to ensure that the bonding jumper is properly installed and that it is protected from corrosion. The bonding jumper should be made of copper or another corrosion-resistant material. It should also be listed for direct burial. Let's discuss the specific requirements for sizing grounding electrode conductors, or GECs, according to NEC 250.66. As we mentioned earlier, the size of the GEC is determined by the size of the service entrance conductors. NEC Table 250.66 provides a table that correlates the size of the service entrance conductors to the minimum required size of the GEC. For example, if the service entrance conductors are number 2 AWG copper, then the minimum required size of the GEC is number 8 AWG copper. If the service entrance conductors are number 3/0 AWG aluminum, then the minimum required size of the GEC is number 6 AWG copper. It's important to note that these are just the minimum required sizes. In some cases, it may be necessary to use a larger GEC in order to meet other requirements of the NEC. For example, if the grounding electrode system consists of multiple electrodes that are located far apart from each other, it may be necessary to use a larger GEC in order to reduce the impedance of the grounding path. It's also important to note that the size of the GEC is based on the size of the service entrance conductors, not on the size of the overcurrent protective device protecting the service. This is because the GEC is intended to carry fault current, not normal operating current. Fault current can be much higher than normal operating current, so the GEC must be sized accordingly. In addition to the requirements of NEC 250.66, there are also some other factors that can affect the size of the GEC. For example, if the GEC is installed in a raceway, the size of the raceway must be large enough to accommodate the GEC. The raceway must also be properly grounded and bonded. It's also important to protect the GEC from physical damage. The GEC should be installed in a location where it is not likely to be damaged by vehicles, equipment, or other objects. If the GEC is exposed to physical damage, it should be protected by a conduit or other protective covering. Let's clarify the distinction between equipment grounding conductors or EGs and bonding conductors. While both EGC and bonding conductors play a role in grounding electrical systems, they serve different purposes. EGs, as we've discussed, connect the non-current carrying metal parts of electrical equipment to the grounding system. Their primary function is to provide a low impedance path for fault current to return to the source, ensuring the operation of overcurrent protective devices. Bonding conductors, on the other hand, connect different metal parts of the electrical system together to create an electrically conductive path. This path helps to equalize the voltage potential between these metal parts, reducing the risk of electric shock. Bonding is particularly important in areas where there is a risk of stray currents or voltage gradients, such as in hospitals or industrial facilities. Bonding conductors can be wires, straps, or other metal conductors. They are typically sized according to NEC Table 250.102, which bases the size of the bonding conductor on the size of the circuit conductors. It's important to note that EGC and bonding conductors can sometimes be the same conductor. For example, the metal conduit that encloses circuit conductors can serve as both an EGC and a bonding conductor, provided that it is properly installed and grounded. However, in other cases, separate EGC and bonding conductors may be required. For example, in a branch circuit that serves a receptacle, a separate EGC is required to connect the receptacle's grounding terminal to the grounding system. A separate bonding conductor may also be required to bond the metal box that houses the receptacle to the grounding system. Understanding the difference between EGC and bonding conductors is essential for safe and compliant electrical installations. Both play important roles in protecting people and equipment from electrical hazards. Let's discuss the requirements for grounding and bonding in specific types of electrical systems, such as separately derived systems. A separately derived system is an electrical system that is not directly connected to the main service. Examples of separately derived systems include generators, transformers, and solar photovoltaic systems. Separately derived systems require their own grounding electrode system. This grounding electrode system must be connected to the separately derived system's neutral point, if one exists. The size of the grounding electrode conductor for separately derived system is determined by NEC Table 250.66, based on the size of the separately derived system's conductors. In addition to the grounding electrode system, separately derived systems also require bonding. All metal parts of the separately derived system must be bonded together, including the generator or transformer enclosure, the raceways, and the equipment grounding conductors. The size of the bonding conductors for a separately derived system is determined by NEC Table 250.102, based on the size of the separately derived system's conductors. It's important to ensure that the grounding and bonding systems for separately derived systems are properly installed and maintained. These systems are essential for protecting people and equipment from electrical hazards. Improperly grounded or bonded separately derived systems can create a risk of electric shock or fire. Now, let's consider the grounding requirements for specific types of equipment, such as motors. Motors are typically grounded through their metal enclosures. The metal enclosure must be connected to the equipment grounding conductor or EG. The EGC can be a wire, a metal raceway, or a combination of both. The size of the EGC for a motor is determined by NEC Table 250.122, based on the rating of the overcurrent protective device protecting the motor circuit. In addition to the EGC, motors may also require supplementary grounding. Supplementary grounding is typically required for motors that are installed in hazardous locations or in areas where there is a risk of stray currents. Supplementary grounding can be achieved by connecting the motor enclosure to a separate grounding electrode, such as a ground rod or a ground plate. It's important to ensure that motors are properly grounded and bonded. Improperly grounded or bonded motors can create a risk of electric shock or fire. Motors can accumulate static electricity, so grounding and bonding helps to dissipate that static electricity. Now, let's discuss the importance of regular inspection and maintenance of grounding and bonding systems. Grounding and bonding systems are essential for protecting people and equipment from electrical hazards. However, these systems can become damaged or deteriorated over time, reducing their effectiveness. Regular inspection and maintenance can help to identify and correct any problems before they lead to a dangerous situation. During an inspection, the following items should be checked. Firstly, all grounding and bonding connections should be inspected for tightness and corrosion. Loose or corroded connections can increase the resistance of the grounding path, making it less effective. Secondly, all grounding electrodes should be inspected for damage or deterioration. Ground rods can become corroded or broken, and ground plates can become cracked or damaged. Thirdly, all grounding and bonding conductors should be inspected for physical damage. Conductors can be cut, frayed, or damaged by vehicles or equipment. If any problems are found during an inspection, they should be corrected immediately. Loose connections should be tightened, corroded connections should be cleaned or replaced. Damaged electrodes should be replaced, and damaged conductors should be repaired or replaced. In addition to regular inspections, grounding and bonding systems should also be tested periodically. Grounding and bonding tests can help to verify that the systems are functioning properly and that the resistance of the grounding path is within acceptable limits. There are several different types of grounding and bonding tests that can be performed, including continuity tests, ground resistance tests, and impedance tests. The type of test that is performed will depend on the specific application. It's important to have grounding and bonding systems inspected and tested by a qualified electrician. A qualified electrician has the knowledge and experience to properly inspect and test these systems and to identify and correct any problems. Taking the time to regularly inspect and maintain grounding and bonding systems can help to ensure the safety of people and equipment. These systems are a critical part of any electrical system, and they should be treated with respect.